This is Unit 4, Lesson 5, Part 1, Linear Approximation. We're going to go into a little more depth of approximating function values using local linearity. We looked at it a little bit in Unit 2, and we're going to go into a little more detail in this lesson so we get a better understanding. So what we want to remember is that we were using the local linearity was really the equation for the tangent line at the given point. So f of x equals f of a plus f prime of a times x minus a. So going through this then, let's go through what we got. So suppose f is a differentiable function at a point a. Then for values near a, the tangent line approximation is going to be our approximation, our local linearization, which is f of a plus f prime of a times x minus a. Now, we are going to define that expression and call it the local linearization. And we're going to give it a letter. So we're going to rename it L of x for linearization. So if we look at a fixed point, and then we're going to look at f of a and f prime of a as being constants. So what we're going to say is that the change in f is going to be f prime of a delta x, where we're just going to be a little bit away. So the change in f is f of a plus delta x minus f of a. And I'm going to show this in a little more detail on the graph. And then as we work with it, it'll probably become a little more obvious what we're talking about. So then we're going to also talk about the error in our approximation. Sometimes it'll ask you how far away your approximation was from the actual value. And those problems are usually calculator problems because you have a complicated function. A lot of times you're going to have to be able to get the exact value of the function. So the error is going to be the absolute value of the exact value minus the approximation, or the change in f minus that little bit of change that we have, that f prime of a delta x. So if we want a percent error, we're going to take the absolute value of the exact minus the approximation over the exact, and then multiply that times 100. Okay, so what does this look like on a graph? So what we have here on our graph is, of course, we have our tangent line, and it's tangent at a specific point here. Whereas you can see, here's f of a, right there, there's our point. And then we're moving a little bit away from a. That's the distance away. So then we have the point right here, okay? And that is going to be our linear approximation. Because that's the point on the tangent line that we're looking for. So let's say a was 1. So this x is like 1.1 or 1.05 or something like that. So that's where it's going to be on the tangent line. So what we notice though is here at this point, we're on the curve again. This is our exact value of the function where we want to approximate it. So this little bit right here, this distance right there, that is our error. That's our error. So that is our f prime of x delta x. Okay, because this is our delta x here. This is how far away we are. And then that's our slope of our tangent line times that little change in x. Okay, so let's go through now the procedures for finding the linearization. And I don't think your head's spinning. So here's what we want to do. We first want to, and we've kind of been doing this already, so we first want to write the point-slope equation for the tangent line. And we're going to rename this equation L of x. So if it isn't isolated for y, we'll have to go ahead and do that. So that's our L of x. Then what we do is we're going to substitute the value in for a in the equation, and we get our local linearization like we've been doing before. I don't know why my pen keeps skipping today, but this is our local linearization. And then what we're going to do is you may need to decide if it's an overstatement or an understatement, underestimate or an overestimate. So what you want to think about is the concavity of the curve. If it's concave up, which is like a parabola that's facing upward, then your tangent line is going to be an underestimation because you're beneath the curve. But if your function is concave down, like a maximized parabola, then the slope, the tangent line, is above the curve, so it's going to be an overestimation. And then you want to make sure if you're asked to find the error, you're going to have to use your calculator. And really what you're going to do is you're going to find the absolute value of the difference between the exact amount and the approximation. And then we state our error that it's 10 to the negative some power if it's a good estimation. You definitely don't want it to be a positive power. So like let's say if you look at the example that's right here, if the actual error is 0.000147, you notice there are 3 zeros here. So that's reported as a 10 to the negative 3 error. But if you wanted a percentage error, you would just change your exact value and multiply that times 100% to get the percentage error. So I think the easiest way to do this is just to jump in here and let's do some problems. All right, so let's look at example 2. The function f is twice differentiable, and where f of 3 is negative 2, f prime of 3 is 5, and then we're supposed to write the equation of the tangent line. So how do we do that? Once we do that, we're then to use the equation to find the value of f of 3.1. So what we want to remember when we're doing this is that f of x, our approximation is going to be approximately equal to our local linearization. So that's what we have to do. The nice thing is, in this function, we have the value of the function and we have the value of the derivative. They told us it was twice differentiable, but in this part, we don't need that. We don't need the second derivative. Now, this problem might have other parts to it that require you to use the second derivative. You might want to have to use that if it asks you about the concavity. We're going to be getting to that in the next unit. How do you use first and second derivatives to determine whether you're concave up or down? But in this problem, we're not being asked if it's an overestimation or an underestimation. So we just have to find the equation of the tangent line and then use that to approximate the value. So what we're going to do is we're going to write that our L of x is going to be our f of 3 plus our slope at 3 times x minus 3. Okay, so our f of x is now approximated as L of x, and that's going to be negative 2 is the value at 3, plus our slope is going to be 5 times x minus 3. Now you can simplify that if you want, or you can leave it like that. So we're asked to find f of 3.1. So that's going to be approximately equal to L of 3.1. And substituting that in, we get so this is going to be negative 2 plus 5 times 0.1. So L of 3.1 is approximately equal to negative 1.5. It's actually not approximately, it's exactly equal to that. So f of 3.1 is approximately equal to negative 1.5. So that's us. That's all we're asked to do in this problem. Nothing more than that. Linear approximations will do a great job if you're really close, and we've talked about that. But what exactly is the neighborhood? So we have to be careful. And that's where the error comes to let us know if we have a good approximation, is how far away we are. So a famous linear approximation is for vibrations, pendulum motions, and other things like that. So if we look at a periodic motion like a sine function, we have y equals sine x at x equals 3. And of course, not x equals 3, at x equals pi over 3. And we know that this is a point on our unit circle, 1/2 comma square root of 3 over 2. And if you were going to approximate the radian measure of pi over 3, you'd get that number 1.0471975. So the reason why we kind of need to know that is, so if we want to find the linear approximation for 1.05. Okay, so just like before, we're going to start by finding the derivative and finding the value of the slope and the value of the function and writing a local linearization. So the derivative of sine is cosine x. So at pi over 3, we have a y prime of 1/2. All right, then if we want to find our local linearization, so we're going to take the value of the function. So we'll put our slope in and do x minus pi over 3. And then we have plus the square root of 3 over 2. So if you were to substitute y equals sine of pi over 3, and that's square root of 3 over 2. But of course, if you know your unit circle, you have the answer right there. Okay, so now we want to approximate f of 1.05, which is pretty close to pi over 3. So this is our local linearization. So we're going to substitute that in. And at this point, you notice your pretty little calculator symbol up there. You can go ahead and do that. So f of 1.05 is approximately equal to L of 1.05. And this time, this is going to be an approximation since we're dealing with pi. So this is 0.86742668. That looks terrible. Let me write that again. I was trying to look at the paper and write at the same time. So 7426682. Now at this point, if there's more that's being asked, I know for the test you only need to keep 2 decimal places, but you should keep as many as you can, especially if there's more parts. Like now we want to find the error. So what we're going to do is we're going to take the absolute value of f of pi over 3 and subtract from that our local linearization value. So this is going to be approximately equal to, if we do all this, we're going to get negative 0.0014. So that's just going to be the positive value. And all I really did was just take square root of 3 over 2 as a decimal and subtracted from it this value right there. And so if we were looking for the error in terms of what power it is, this is going to be less than 10 to the negative 2. So that's pretty good. So I'm going to stop here for the first video and finish up in the next one.